So welcome everybody to today's seminar. Today's auspicious April Fool's Day, and we have a very nice speaker today, Toby Wiseman, who needs actually no introduction. What he's specially going to talk about is a very nice colloquium, introduction to his work on holography, testing holography on the lattice. So let's hear from him now. So over to you, Toby.
Thank you. Thank you very much, Ian. Thank you for the invitation to speak. Indeed, I'm going to talk about using lattice field theory to try and understand better quantum gravity and black holes through the sort of framework of holography. And I'm going to talk actually not only, I thought I'd, it seems appropriate to talk about the sort of whole field as well as some of the work I've done recently. But I think probably, I'm not so sure people are very familiar with this story. So I think I'll spend quite a lot of time with introductory or hopefully a pedagogical introduction. And I would definitely encourage people to ask questions if you have them. It would be very nice to have some questions. So I'll talk about lots of people's work, but in particular, I want to thank my collaborators. So there's Simon Catterall, who I've worked with for many years on this, and more recently Joel Geet, Anos Joseph, Raghav Jha, and David Sheikh. And particularly for the recent work that I'll talk about at the end, Raghav and David have really done all the heavy duty numerical side of that. So they've worked very hard indeed and done a brilliant job. So let me tell you a plan for the talk then. The idea, the goal of the program is to sort of directly simulate quantum gravity using lattice. And so I'll start off by talking about holography. Now, of course, many of you are experts on ADS-CFT and holography, but we're going to be using holography in a slightly different setting than the usual ADS-CFT story. And I've found that people tend to be less familiar with that. So I think it's worth reviewing that, even for the experts. And then I'll talk about black hole thermodynamics in that setting. And then I'll talk briefly about the lattice. I don't know how many of you are sort of lattice experts, so I'll say a few little bits about it. But if you want more details, please do ask. If I'm saying things that are too obvious, then just tell me and I can move on. But once I've got through the introduction, then I'm going to talk about mainly old results, some newer results associated to a low dimensional version of this lattice field theory, which you can simulate, which is actually just a quantum mechanics. It's the old Bfss model, and tell you what you can do in terms of understanding black holes in that system. And then I'll talk about higher dimensional cases in 1+1 and 1+2, which is where I focus my more recent work, and tell you what we're doing there now, or in recent years. Okay, so as I say, please do interrupt if you have questions. Let me start off then by just reviewing holography. As I say, many of you are totally expert on this, so so I'm going to emphasize the aspects that are relevant in our situation that are a bit different to the usual ADS-CFT situation. So Maldacena, as you all very well know, said that certain maximally supersymmetric gauge theories, those living in P+1 dimensions, SUN or UN gauge group, that's the world volume theory at low energies of ND brains, DP brains, I should say. So these are DP brains, not just D3 brains. He actually did this general version shortly after ADS-CFT. And the idea is that this is equivalent to the decoupling limit of string theory in the background of these brains. And so there are two apparently dual descriptions. One is this Super-Yang-Mills description that sort of lives in the world volume. And the other is this gravitational, by gravitational, I mean there's dynamical metric, I should say. There's a sort of gravitational string theory description where the brains, because there are many of them, they cause the geometry to back react and develop an infinite throat. In fact, if we turn on finite temperature, that gets cut off at some finite distance down in it, but it's a very long throat. And the idea in the decoupling limit, the way holography works, is you're focusing on the degrees of freedom that live down this throat. So the statement of holography is really that because there's this infinite throat, there are degrees of freedom that live down there, that are localized down there, and it's those that are described by this gauge theory. That's the idea. Now, at finite temperature, as I said, we would develop a horizon, so this would become a black hole, and over here in the Yang-Mills theory would just be finite temperature field theory. Now, we'll be working in the 't Hooft large N limit, and we need to do that in order to get gravitational control here. And so the natural coupling is this 't Hooft coupling. And something to note that's sort of less familiar is that when you're not in P equals 3, which is the usual ADS-CFT case, and we won't be interested in that case here, we'll be interested in P less than 3, then the 't Hooft coupling, the Yang-Mills coupling, have mass dimension 3 minus P. So that's something to bear in mind. Okay, so when you look at the degrees of freedom that live down this long throat, they see an effective metric which sort of traps them in the throat because they've got low energy, they can't escape. And so the effective metric they see has a conformal boundary, and they want to fall into the infrared. So of course, this is the ADS boundary if you're in P equals 3. If you're in P less than 3, this is some other conformal boundary. It's got a slightly more complicated structure because you have a dilaton that isn't constant. But nonetheless, it's the same idea, it's the same physics. Now, in this situation where P is less than 3, the dilaton increases into the infrared of the geometry, and therefore we need large N to control things in order to control, to keep the string theory sort of, keep the G string corrections small. And alpha prime corrections instead become relevant near the conformal boundary. So again, it's slightly different to ADS-CFT. So there's a sort of spatial dependence as to which corrections become important in which region. So the idea is that if you are at large N, you may have a region down here where it's well described by 2A or 2B supergravity. But if you go near the conformal boundary, it won't be, okay, because of alpha prime corrections. And you can, as I'm sure you're all very well aware, write down explicit metrics for this effective decoupled geometry. And the P equals 3 version, of course, is the famous ADS5 cross S5. On the
can
gauge,
I ask you something here on this slide?
Of course you can.
So there is a similar story which was told by Maldacena, and he was, I forgot who were the other co-authors. He was saying that I think the title of the paper was to gauge or not to gauge the matrix model. And he was claiming that the singlet sector can describe without even can describe supergravity.
I'll come on to that later.
So,
yeah. Let me come on to that later. Yeah. So this is I'm describing here the original old ADS-CFT story from, I can't remember, 98 or so. So this was, Maldacena first discussed the P equals 3 case and then had a paper almost immediately after discussing the general P case. So the decoupling limit of DP branes. And this is that very old story. I'll certainly come on to that more recent idea. Anyway, in this case, the gauge theory looks like the generalization of the usual n equals 4 in 3 plus 1. When you're in P plus 1, in fact, it follows from n equals 4 trivially by just classical dimensional reduction on a torus. So if you want to go down in dimension to P equals 2, 1, or 0, you can just dimensionally reduce the flat space n equals 4 theory on circles. And that gets you this theory when you do that. So in the P plus 1 dimensional case, you have 9 minus P scalars. And, 9 minus P scalars, you have your fermions as usual, you have your interaction term here, you have your gauge field, and so on. Everything, the scalars and fermions are transforming in the adjoint. And so we can think of them as n by n matrices. Now, the temperature is, of course, dimension full, but our coupling is now dimension full. So in this situation, when we turn on finite temperature, as we'll be doing here because we're interested in black holes, there's a natural dimensionless coupling, which you form by basically taking the temperature in units of the 't Hooft coupling. So I'll call that little t, that's dimensionless. And if we come back to this picture here, we know that we get alpha prime corrections up in the UV of the geometry. And so in order to describe using usual black hole thermodynamics, the thermodynamics of a black hole here with a horizon, we want the horizon to be sitting far enough down in the infrared that the geometry near it is well described by supergravity, not alpha prime corrected supergravity. And that tells us that we basically need the horizon to be far down in the infrared, which in this 't Hooft limit tells us that we need this dimensionless coupling to be less than 1, or much less than 1, okay, in the large n limit. So just to be clear on limits, I'm talking about taking n to infinity, keeping t finite, say scaling as n to the 0, order 1, and then taking the numerical value of this dimensionless t to be small, say 1,000th, ideally 1,000,000th, something like that. Okay, but once you've taken n to infinity, that's the order of limits. And when you do that, Maldacena, in his very early works, computed the energy density, epsilon here. And this here is the energy density for these black holes. Obviously, it's a function of temperature. And there's some very explicit form, which is absolutely precise. So that's a precise prediction for the thermodynamics in this regime for this Super-Yang-Mills theory. And parametrically, it looks like this. So you have an n squared dependence, which is what you expect, I suppose, naively. And you have some rather peculiar power law dependence on this coupling T. And then here we have lambda just makes up the units in this expression. Now, this power law dependence on T is a little bit mysterious. If people are interested, I can say a few more words about it, but it's not well understood. The n squared here, you might say, well, of course, there are n squared degrees of freedom in this theory, but in p less than 3, the theory becomes strongly coupled in the infrared. Remember, the gauge coupling has a classical dimension, which runs to become, strong in that sense in the infrared. And so, and because we're interested here in the infrared, it isn't a priori obvious, actually, that you should have n squared degrees of freedom, effectively in the infrared. It's a strongly coupled system, so it could have done something else. Another thing I want to emphasize, and I'll come back to this in a minute, is that if you calculate the entropy from this energy density, you find, again, it goes like n squared, and there's some power of t, and in particular, it goes to 0 as we take t to 0, okay? And just in pictures, as we vary this dimensionless coupling T, this dimensionless temperature, what we can think of as happening in the dual geometry is when T is small, we have a long throat ending on a horizon, and there's a big region near the horizon where 2a, 2b supergravity is good. But if we try and take T to be order 1 or even large, the horizon, well, in principle, it's still there. It's close enough to the conformal boundary that it's very alpha prime corrected, and you lose control over understanding what it should do. And so, as I said, the goal of all of this then would be to try and reproduce this. I mean, that's perhaps the most basic goal. The starting point is, can we get this from this finite temperature Super-Yang-Mills? If we can do that, then we can be sort of confident that this conjecture of holography is well, we can be more confident it's correct, and maybe we can calculate other things that we want to understand. But I think the starting point is just to see that this comes out. And of course, there's a very long story of calculating thermodynamics of black holes and string theory, calculating entropy of black holes, which goes back, I mean, over 20 years now. And it's a very beautiful story with lots of recent progress, but it is all focused on counting ground state degeneracy. So the situations in string theory where you can count black hole entropy are either where there's some Cardy formula that allows you to do it because secretly there's an ADS3 and a dual CFT2, and you can use the ideas of Cardy, or you're counting ground state degeneracy. So all this precision counting is really associated to counting microstates, where you're in a situation that you've turned on some potentials or charges, and that forces you to have a highly degenerate vacuum, or vacuum, or rather ground states, not vacuum, but ground states. And then you have some method of counting those. Now, I just want to emphasize in this situation, this is very different. Here you see the entropy goes to 0 as T goes to 0. So the entropy here is really a thermal entropy. It is nothing to do with ground state degeneracy. There isn't any. So in these lower dimensional P's, say in P equals 0, it's believed that there's a unique ground state in this theory at 0 temperature. And so there isn't any entropy, at least in the simplest cases, at 0 temperature. So that's not the entropy we're trying to get at. And I think it's just important to make that point. This is not the same as the usual entropy counting that's done in string theory. So this is a sort of harder version in a sense, because it's really to do with being at finite temperature. You really have broken supersymmetry. You can't use any of these nice tools that are used in the microstate counting usually. Okay, so it's more like the sort of entropy that we believe something like Schwarzschild would have. So maybe I should pause for if there are any questions before I go on. Do let me know. Okay.
So on the Yang-Mills side, you have to incorporate alpha prime corrections if you're going to do any match, right? Because you have a long throat, gravity works in the infrared.
I see. Yes, absolutely. So
yes, this Lagrangian will get corrections, right? The Lagrangian you're showing.
Oh no! In the decoupling limit, this is the Lagrangian. So okay. This is like the usual ADS-CFT story. So in the decoupling limit, you don't have any, all the high derivative corrections to this have gone because you focused on the low energy excitations. However, as you say, this is describing all of these situations. So that Lagrangian should describe all of the physics here, the alpha prime corrected physics and the low energy physics that doesn't get alpha prime corrections. I mean, that's the idea. So so the prediction would be for low temperatures, we should recover this supergravity behavior. But if we increase the temperature, we should see in the super Yang-Mills some sort of alpha prime corrected behavior.
Okay.
Yeah, that's right. Thank you.
Toby, I actually also have a question. I thought you said T has to be small, but why should it be smaller than 1? Stupid question, probably.
Well, I mean, I'm not sure I totally understand. So T is the temperature in units of the 't Hooft coupling, and when you work out how the alpha prime corrections, I mean, there aren't any other scales really. So alpha prime corrections can only come in powers of T.
Okay,
so by taking T small, you're basically, if you could calculate alpha prime corrections to this leading supergravity behavior here, they would come as some power series in T with some positive powers.
That's exactly what I was asking. Yeah. So you expect some power series T corrections without any alpha prime explicitly.
That's exactly right.
So you expect, so that those will be the subleading effects.
Yes, exactly.
And will the subleading effect be also proportional to? So is it also proportional to n squared, updating effects?
Yes, I believe so. Yeah. I mean, I think one way to understand that is it's a bit like you're in the deconfined phase of the gauge theory. So you expect some behavior like, you know, you expect quantities to go like n squared. So you would expect, it would be rather surprising if the leading behavior went like n squared and the corrections didn't. But I mean, I'm not sure I have any proof of that, but I mean, that's the expectation. And certainly in the gravity, from the point of view of gravity, you could, in principle, calculate these alpha prime corrections by perturbing about this leading supergravity solution with some high derivative terms. And if you do that, you'll get corrections to the energy. You can calculate perturbatively the corrections to the energy, and they will certainly come in with an n squared and be expressible as some powers of t. Yeah. So provided that that picture is all correct, yeah, that's right. Good.
Thanks, yeah.
So a few words then about lattice, the lattice. Because we're interested in finite temperature, the lattice is very effective. So obviously we can think of finite temperature by thinking about Euclidean field theory, where we just make time periodic with period beta, the inverse temperature. And in that situation, usually the lattice is a very powerful tool for simulating the path integral. So the Lorentzian path integral, we can continue to the Euclidean. And then typically one has some real Boltzmann weight, and one can use Monte Carlo methods to importance sample the this partition function, now this finite temperature partition function. Now, because we have a supersymmetric theory, there's the extra challenge of fermions, and those challenges come in different forms. You know, fermions sort of traditionally strike fear into the hearts of people thinking about the lattice, but for different reasons. So there are sort of in principle problems. So for example, chiral fermions, it's an in principle problem how you put them on a lattice. We don't have chiral fermions here, so there's no in principle problem with putting fermions on the lattice. It's well understood how to put sort of standard fermions on the lattice. It's not hard. It's technically requires a lot more computation because basically your theories become non-local. But when you do that, I'll describe it shortly or sketch why. But there are a couple of subtleties in the supersymmetric case. One is that we require obviously supersymmetry in the continuum limit of this lattice theory, and you have to worry about whether there are tunings you have to perform in order to get the right continuum limit. So the lattice will typically break, you know, all the symmetries, supersymmetry included, and the question is, do you recover that in the continuum limit? And there's another in principle issue, which is the so-called sign problem, which can be associated to fermions, and I'll talk about that in a minute. In fact, I'll talk about that right now. So the way we normally deal with fermions on the lattice, or one way to deal with them, is you can recast them as non-local bosons. So the starting point is that you integrate out the fermions and you get some sort of Pfaffian of some operator, in our case. Now, immediately we run into a problem that this Pfaffian, what we'd like to do is sort of re-exponentiate it into an action or rather simulate it using some bosonic degrees of freedom. However, this Pfaffian, it turns out in these supersymmetric theories, isn't real positive. And this gives rise to what would typically or potentially be called a sign problem. And so the issue is that Monte Carlo methods work very well with a real Boltzmann weight. But if you have a complex weight here, they're hopeless. They don't work at all. Or rather, yeah, you completely lose control, which is why you can't directly simulate on the lattice Lorentzian theories. So what we do is we, instead of calculating or using our importance sampling with the correct weight in the partition function, where we correctly have the Pfaffian, we instead do what's called quenching the phase. So we can generate configurations instead with a weight that's given by the norm of the Pfaffian, so killing the phase. So we write the Pfaffian as some phase times this quenched Pfaffian. And then formally, once you generate correctly an ensemble of configurations with this quenched weight, if you want to calculate some observable, you can do it by summing it over this ensemble, but reweighting each configuration with the phase that that configuration has and appropriately normalizing. So this is called reweighting, and it's one way to deal with having a so-called, well, a sign problem or a weight in your partition function that isn't real. However, the key issue is that this is a formal expression, but it's far from clear that it's going to converge. And in particular, if you have lots of phase fluctuations between configurations in your ensemble, you can see that the denominator here is likely to be very poorly behaved in terms of convergence, and the whole thing will probably not make much sense. And so this really is only an effective way of proceeding if the phase doesn't fluctuate too much. And as I say, this comes up commonly in other situations, like QCD at finite density has a sign problem, and it's a big issue on the lattice how to deal with this. And there's lots of sort of interesting ways, other techniques, not Monte Carlo, other ways of doing things that are sort of focused on trying to understand how to deal with the situation, because it can be so challenging. But let's assume for now that we're not going to worry about this, and we'll just work with this quenched phase and hope that we don't miss too much physics, or we can put it back in by reweighting like this. How do we then proceed? Well, this quenched Pfaffian you can write as a determinant with some fractional power. And then you simulate that on the lattice using, as I said, bosonic fields. So what you do is you introduce some bosonic fields, and then with this action, where, of course, now when I integrate out these bosonic fields, I get this determinant back. But the key point is that I've got some inverse power here. So this is a non-local bosonic action. Oops. And that's in a sense where the technical challenge of fermions come in. Even if you didn't have the sign problem, it just, in this way of dealing with them, it makes the action non-local. And many of the simplest Monte Carlo methods work very well on local actions, but not on non-local actions. But there are more sophisticated ones that work pretty well on non-local actions. And that's the sort of thing that we're using here. So you deal with this fractional power by expanding an irrational fraction approximation. And then you have some non-local action. And in this form, there are efficient ways of inverting this operator here, this in the denominator, and sort of evaluating this term. And one can use non-local or algorithms to do this Monte Carlo simulation that work well with this sort of non-local action. So in particular, there's this hybrid Monte Carlo algorithm. And so that's really how one in practice simulates these theories. So I'm now going to go on and describe some of the results that you get when you look at this, but maybe again I should stop and just check if there are any questions. Don't worry if there aren't.
Toby, I just want to go back to my earlier question. So then
Okay.
epsilon, your n squared times lambda some power and some function of t. If I take this order of limits, and I see.
Yeah.
So somehow you want to actually obtain this function of t from the lattice.
Yes, so actually what we want to do is not just get this function of t, but we want to get the coefficient as well. Yeah, we'd like to get the whole thing. I mean, that's the grand idea.
Yeah, so but this is only the t, but in principle you can also get the subleading ones. and which you can check with higher derivative corrections.
Yes, if you have enough control that you can calculate the high derivative corrections and their coefficients, then indeed, that's right. I mean, so at the moment, I think it's fair to say that we can't calculate precisely the coefficients of those high derivative terms. So I think it's known. You know, you can get the corrections in powers of t. You can get just by understanding that they come from some high derivatives, but without knowing the explicit coefficients, which require some complex string theory calculation in you know, in these backgrounds. It's you can't, well, all you can get is how the various terms will go. You can't get the precise terms themselves.
Okay, thanks.
Yeah, we'll see this now actually in practice. Oh, sorry. Yeah, sorry.
Could I ask for a quick clarification?
Yes.
I didn't quite understand. Could you please go back to the slide where you say that you take care of the phase?
Yes.
With the mod of the Pfaffian, are you averaging over configurations and then again averaging over configurations with the phase phi? I didn't quite get that.
I see. No,
the order of the steps are there.
Yeah. So normally, if you could calculate correctly with the proper Pfaffian, you wouldn't have the denominator here, or yeah, the denominator would just be the number of configurations. And in the numerator,
no, I understand that. What I'm saying that in the numerator you have this A. Is that already averaged over configurations? What do you do with the mod of the Pfaffian?
A is just the operator. So this is the operator evaluated on the configuration.
Yeah, but
so
with
sum.
Just a particular. So for the mod of the Pfaffian, you calculate it for each configuration separately and just leave it to put it in this formula now?
So the ensemble is calculated with the weight, the Boltzmann weight, if you like, involving only the mod of the Pfaffian, not the full Pfaffian. And now
for each configuration, in each configuration you do that. And then
you generate configurations with the correct frequency, if you like, or you generate an ensemble whose configurations have the right statistics, that they've come from this partition function, whose weight is this quenched Pfaffian, together with the bosonic action as well. Okay. Now, then you have to, when you sum up your, when you calculate an observable and average it over these configurations, you have to put back in the phase for each configuration.
Mm-hmm. Okay. Well, I guess it's a complicated process. I was just trying to understand when I understand the logic that you're trying to do, but I don't see that in the formula, the way it's written. Anyway, it's not important. I think I can still follow without that. And the other question is that this non-local operator, is it meromorphic or is it holomorphic? Does it have poles or cuts or anything on as a function of momentum or derivatives or something?
I mean, we're on a lattice, so I'm not sure, you don't have a continuous momentum. So I'm not sure. I'm not sure.
You still have, well, on the lattice, you're putting a cutoff in real space, but the momentum will have Brillouin's on side. So then we continue values of momentum, or are you also?
Well, I mean, so you have a cutoff in space, and you'll also typically have some finite size as well. So there's both an infrared and a UV cutoff. To put a lattice on a computer, there has to be a finite number of points. Yeah. So I think in the continuum, yes. I mean, in the continuum, this operator is just the Majorana fermion operator together with the gauge interaction.
So that will have some poles. That will have some poles. Okay.
That will certainly have some poles in the continuum, but on the lattice, I think it's complicated.
Yeah. Okay. Thank you. Thank you.
Okay. Good. Okay. So let me now.
Toby?
Yes.
there was this on the slide. There was something written which you didn't comment on. This rational function fraction approximation.
Oh, no, that was just a technical point about how you deal with these fractional powers.
Ah, okay, I see.
So remember, this is the fractional power of some horrible matrix when you think about it on the lattice, and you deal with it by approximating this using a rational fraction approximation, which works very well. Well, by taking enough terms in your rational fraction approximation, you can make it an extremely good approximation over the range of sort of eigen, over the range of space of this operator where your configurations are going to live. So basically, given some range of eigenvalues that you are likely to be probing in your lattice, you can take enough terms here so that over that range, over that eigenvalue range, this is a good approximation. So it actually works remarkably well.
What's the typical lattice size that you use in?
Well, I'll come on to that. I'll come on to that.
Sure.
Yeah, I'm going to show some results now. So let me, in fact, I'll come on to it in a couple of slides. Let me just say a few more words. So let's start with this, the simplest case, which is this P equals 0 model, which is the old Bfss model. So this is going way back. And so the Bfss model is just the quantum mechanical version of this. It's quantum, gauged quantum mechanics. And the idea, again, is that at high temperature, it's going to behave just like quantum mechanics. And quantum mechanics will tell us that the energy, it's now not an energy density, it's just an energy in the quantum mechanical case. The energy is obviously going to go like the number of degrees of freedom squared times temperature, just on sort of counting degrees of freedom and dimensional grounds. But at low temperature, and by low I mean in this regime, we expect the supergravity to prediction to hold, where this becomes even sort of strongly coupled, and we expect this specific behavior, okay, with corrections in higher powers of T. So there are some simple observables to look at. One is obviously this energy, and that can be calculated, if I just move that can be calculated as in here from the expectation value of the bosonic action. So basically the fermion action, the fermion part of the action, because it's quadratic in the fermions, is trivial. You can just integrate them out. And it just, so the expectation value of this just gives some constant. And the interesting dynamics is really in the expectation value of the bosonic action. And it turns out you can relate that to energy over temperature. So
Toby,
now, yes. Sorry?
Lambda to the power 1/3 missing in this equality that you have put in the box.
Oh, I'm so, yes, I'm so sorry. There indeed, you're absolutely right. Sorry, thank you. There should be, I think I can add it like this. There should be a lambda here to the 3rd. You're quite right. Well spotted. Oh, no, it's gone. Okay, anyway, thank you. Indeed. Oh, there we are. Yes. Now, the other observable that you have is the holonomy of the gauge field around the Euclidean time circle. And so this is an element of SUN, and therefore the eigenvalues lie on a unit circle in the complex plane, that is phases. And at large n, there are lots of them, so we could think about the distribution of the eigenvalues on this circle. And Witten, long ago, told us that we should think of that eigenvalue distribution as diagnosing whether there is a horizon or not in the dual geometry. So basically, if the eigenvalue distribution on the circle is uniform, then we should expect there to be a horizon. And if it isn't, we should expect there not to be a horizon. And if it's not uniform, it's got some interesting configuration on the circle, then we would expect there to be a horizon. And basically, it's because the trace of this holonomy, calculated like this, is related to whether a string world sheet exists in the dual geometry with some finite action. And that's related to whether the Euclidean time circle caps off in the bulk, and therefore whether there's a horizon or not. So there's some relation, but the basic point is we've got this, the eigenvalues of this holonomy can diagnose confinement, deconfinement phase transitions in the gauge theory, which are related in the field theory to whether there's a black hole or not. So this is the analog, for example, in ADS-CFT of the usual Hawking-Page transition. One could diagnose it by looking at the holonomy of the gauge field around the Euclidean time circle. And at large n, one would see a transition, a phase transition in the behavior of the eigenvalues. I've got some comments here, but I think in the interest of time, I might not discuss these issues of the partition function. But just let me just say that actually in this theory, it turns out that it's the thermal partition function doesn't exist. So it's a perfectly good theory. There's supposedly a unique ground state in this theory. But when you try and put it at finite temperature, formally, the partition function doesn't exist. And it's basically, in sort of stringy way of thinking about it, this describes n d0 branes. And if you separate the d0 branes far apart, they basically don't feel each other. Now, this decoupling limit that we're interested in, all that physics is coming where the d branes all sort of bind together in some strongly interacting state. But if you separate them far away, they don't interact. And so, and because of that, if you try and put the system at finite temperature, if you've got a sort of bound state of these d branes, some can always escape. There's always some chance that they get kicked out from the bunch. And then when they're gone, they're gone. So really, actually in this, it's believed that at large n, what you have is a metastable bound state or a metastable vacuum, but it's not the true vacuum. But it's that metastable vacuum that we think describes this black hole physics. Okay, and there's a way of curing the fact that there's only a metastable vacuum, which I'll come to later. But certainly in the early simulations, it's that metastable behavior that we're trying to explore. Just to emphasize, there's no problem, you know, many theories don't have a good thermal partition function. A sort of canonical example would be the hydrogen atom potential, which of course is a perfectly good quantum system. It's got a good ground state and so on. But if you try and put it at finite temperature, it's bad because of the infinite volume. So the electron will always want to escape out of the hydrogen atom to infinity and won't come back. So you have to sort of, if you want to treat an electron in a hydrogen atom potential or a particle in a hydrogen atom potential, you would have to put it in a box to regulate that divergence. And there's an analog for this theory, which I'll come to shortly. The other thing is, Ian mentioned this earlier, there was very interesting recent work by Maldacena, who said that actually this black hole behavior at low energies or low temperatures, or he conjectured, isn't dependent on the fact that this quantum mechanics is gauged. So his claim is that if you take this theory and just kill the gauge field dynamics, which in a quantum mechanics, all the gauge field really does is project you onto singlets states. If you just ignore that, this theory, he claims, still has this same low energy behavior. And the idea is that the non-singlet states are very massive, and so they're associated to changes in the UV of the geometry, but that's not what we're interested in. We're interested in the IR, where the supergravity is good, and so his claim is that that's not affected. You know, killing the gauge field doesn't change things. And there's some recent numerical evidence, or around the same time, by Berkowitz and Hanada and collaborators, sort of confirming this. So I think that's very interesting. When you try and put this theory on the lattice, it's very easy because it's just quantum mechanics. You don't have any issues with fermion doubling in quantum mechanics unless you do something sort of silly. And it's possible to have divergences with fermions in quantum mechanics from loops like this. And there was a very nice sort of paper discussing this. So if you just put a simple supersymmetric quantum mechanics on the lattice, actually you don't get the right supersymmetric continuum unless you do a fine tuning. What these loops do is they change the mass between the lattice theory and your continuum theory. They change the mass between the scalars and the fermions, sort of ruin the supersymmetry. However, actually in the gauge theory, these interactions vanish because of the vertex gauge, the structure of the vertices due to the gauge symmetry. So it's a bit like in QED where these sort of tadpoles, don't contribute because of the gauge structure. And it's the same thing here. So in fact, a naive discretization, provided you don't do something silly and introduce fermion doublers, will actually give you the correct continuum physics in this quantum mechanics. So it's very simple. And these are very old results. These are going back a very long time. This is work of mine, Simon Cattrall, and a group led by Jun Nishimura in Keck. So we simulated things on the lattice, and I quite like this plot down here. Coming back to the question, this is a 10-point lattice, so it's 10 points going around the Euclidean time circle. So very small, but this was the early work. This is, I think, only n equals 5, so SU5. Although we did manage to get higher n's in those days, and in fact, this group got much higher n's up to n of 17 for some set of data, some sort of limited sets of data. But actually, already once you get to reasonable n, already n of 5 is not far away from the really large n limit. It approaches the large n behavior quite quickly. Now, what we see here is this is energy over temperature, energy density over temperature. And again, sorry, Ian, I think this is energy in units of the Tuft coupling again. So I've again, my conventions are wrong. There should be another lambda to a third here. And it's plotted against temperature on the x-axis. Now, when temperature is reasonably big, you expect some sort of linear behavior of energy with temperature, and that's indeed what you see. But as the temperature becomes smaller than 1, you should see, if holography is correct, turning over to this behavior here. This is this black hole behavior. And indeed, it is true that the data seems to be consistent with that. So it does start turning around and come down, and presumably, if you could work at very high n and very accurate on the lattice, you would see it really come onto this line. The same was seen by this other group. So they saw, this is not dividing by t, so they see this linear behavior here as really as linear. And then they see the points coming down onto this black hole curve. This is a zoom in on this section. Okay.
Sorry, Toby, can I ask something? Yeah. You said that formally the thermal partition function doesn't exist. But
so this is this metastable. Yeah. So this more precisely are simulations where you're in this metastable thermal behavior, and you've seen no sign of decay of that metastable vacuum. So something I should have also said is that at large n, it's believed that this metastable state is very long-lived. So the way to understand that is, a sort of intuitive way to understand it is that you've got this clump of n d branes sort of thermally excited doing their thing. The more there are, the harder it is for one to escape because they're all interacting with each other. So if you've only got a few, it's relatively easy for one to get kicked out and not come back. But if you've got a lot of them, they're really strongly bound together. So there's a bigger potential barrier for it to escape. In fact, you can do some sort of estimate of the potential barrier. So Shiraz Minwala had a paper a number of years back by looking in this was in the, I think just the ADS CFT case, the P equals 3 case. I can't remember, to be honest, but you can take a thermal black hole background and then ask for a probe D brane what the energy is for it to escape out to the UV. And so that basically gives you some estimate for the tunneling potential for a brane to escape out of the decoupling region. So meaning to go away from this clump of D branes and evaporate off. Okay. So in these simulations,
get it. Yeah. So you're in Euclidean time, right? I mean, how do you know that you're in Euclidean time? So how do you know that you are counting metastable configurations only. So,
well, okay, that's a good question. So on the lattice, if you have a metastable phase in real time on the lattice, if you simulate it at finite temperature, you would expect to probe configurations that are relevant for that metastable phase for a long time. But if in the end, your lattice should, your Monte Carlo simulation should understand that that actually isn't the true vacuum. The true, or I mean the true configurations that dominate the partition function is something else. And the Monte Carlo method is exploring all configurations. So eventually it will start to find these other configurations. And so what you see on the lattice is that, if you look at the eigenvalues of these scalars, tell you roughly where where the D branes are. You can think of them as in that sense, roughly speaking. It's not precise. And when you're simulating your configurations, you see that the eigenvalues are all tightly bunched together for all the configurations you're generating. But if you run for a very long time, at some point, one of the eigenvalues suddenly wanders off and becomes large compared to all the others. And when that happens, actually, from the point of view of the lattice, your simulation breaks because, basically because the autocorrelation times between configurations become very, very large. So it's sort of hopeless. You can't simulate in that regime anymore. But provided you restrict yourself to only simulate before that happens, and it's like a phase dynamical phase transition on the lattice. There's this phase where they're all bundled together and the configurations are all in this chunk, and then something happens and they wander off. So there's a sense in which you can tell whether you're exploring this metastable phase or you're exploring this other region which really dominates the path integral, but is difficult to reach when you're in the metastable phase. But let me come on, because there's a way of fixing this, which maybe I can get to now. So let me just say, this is old work. And more recently, there have been much more sort of impressive calculations. The group of Berkowitz, Rinaldi, Hanada have done some very nice work. O'Connor and Filev have done nice work, and Cadeau and Kamata have done some very nice work to much larger ends, so up to say 32 here, larger lattices, and so larger lattices in terms of say 30 points around the Euclidean time circle, which is quite a lot in the quantum mechanics, and again you see the same thing. So energy over temperature, you see this linear behavior changing to be consistent with this dash line here, which is this black hole behavior. So it really does seem that at low temperature, you're getting the right behavior. I won't go into this, but you can look at the Pfaffian phase. Once you've generated your configurations, you can evaluate the phase in them, and you can see, are phase fluctuations big or small? Is it reasonable to do this reweighting procedure? It turns out the phase fluctuations are very small in all of the simulations done so far. And it's not really understood why, but it's just true. And what that means is, in fact, typically the error that you get by ignoring the phase in the Pfaffian is much smaller than the error that you have just from statistical error in your lattice simulation. So it's very good, because otherwise it could have been disastrous for all of this. But it's not really understood why the phase fluctuations are very small. So in particular, this is a plot basically of the phase fluctuations over temperature, and 1 is no phase fluctuation. And there is some phase fluctuation at intermediate temperatures, but it actually becomes very small at low temperatures. And it may be to do with supersymmetry sort of being restored at low temperatures, but it's not well understood why this happens. Now, let me just come on to this issue of the partition function existing. There is a deformation of this theory that means that the partition function does exist. It's like putting the D-branes in a box and sort of getting rid of this infrared divergence in the partition function. So in particular, there's a specific mass deformation that you can do where you add masses to the various scalars and fermions in a way that treats 3 of them differently from the other 6. And it preserves all of the supersymmetry. It's the so-called BMN deformation. It preserves all of the supersymmetry, and it preserves the fact that there's a gravity dual, which is sort of remarkable. And it breaks the flavor symmetry down this way. And from the gravitational point of view, so from the point of view of the field theory, it's very simple. It's just the masses. From the point of view of the gravitational theory, the dual gravity theory becomes much more complicated, because what was a spherically symmetric black hole gets deformed to only have SO3 cross SO6 isometry. So it's no longer spherically symmetric. It's more like a sort of axial symmetry. So it becomes, instead of in order to find these black holes, instead of solving some ordinary differential equations, you have to solve partial differential equations. So it's considerably more complicated. George Santos and collaborators worked very hard using numerical GR techniques to actually construct the black holes, these finite temperature black holes. And so here, this is the sort of mass deformation. They can, obviously, you know what the black holes are at low mass, but they were able, or at 0 mass, they're just the previous ones, but they were able to construct the branch as a function of adding this mass. And they found that at some point, you get a phase transition to a confined phase, where the black holes are now not favored over just the vacuum geometry without a horizon. And so there should be a first order deconfinement phase transition. And coming up to sort of quite recent work, O'Connor and collaborators have actually looked at the phase structure, doing simulations in this mass deformed theory. And here, these dots are where they estimate the phase transition to be in this T temperature mass plane. The gravity regime is down at low temperature, as we had before, and low mass down here. And what they indeed see is they see some sort of phase transition, this deconfinement phase transition coming down. And this red line here is actually the prediction from this phase transition from the gravity. So what they're seeing is some sort of phase transition that looks, reasonably consistent with tending to this slope, tending to have a linear behavior with this red line slope down at low temperature and low mass. So that's pretty nice. I mean, it would be great to understand that better or have better data on that, but it looks like what's expected from the gravity is indeed happening in the gauge theory. And just to emphasize again, because you have a mass in this theory, there's no longer, the D branes are really confined in this potential. They can't wander off. And so there is no issue with partition functions not existing here. So this is a cleaner situation. If these days, I think if you want to simulate in this quantum mechanics, that's the situation to do it with that mass deformation. Now I'm over time already, I think. But I've got lots more to say, but sorry, there's a question.
10-15 minutes more. I mean, is it fine?
It's fine for me. As long as it's fine for you.
Yeah, I mean, it is. This is okay for us.
Okay, fine.
So the question is, maybe you're going to mention it again later, is about this fuzzy sphere. So you expect there would be on the matrix model side, you would get fuzzy spheres at low temperature, and then you model it on supergravity.
So I think the expectation is in the black hole phase, I think there's just a single black hole. But when you go into this confined phase here, that's the phase where there are multiple fuzzy sphere vacua. And in the gravity, you have these LLM geometries correspondingly. So quite what the dynamics is in this confined phase, I think is, I mean, I'm not quite sure what the how well understood that is, but because it's a quantum mechanics, I mean, you have these discrete fuzzy sphere vacua, lots of them, but because it's a quantum mechanics, of course, it will do some sort of dynamics going around, at finite temperature. At any finite temperature, it'll sort of wander around these vacua, and so I'm not quite sure how to understand the gravity dual in that context. I'm not sure it's well understood.
Yeah,
but the claim is that in this deconfined phase, the black hole phase, there's just a single black hole dual. I mean, that's I think the current understanding. There isn't a sort of fuzzy sphere's worth of them. Yeah, and they see that in these simulations. They see that in the deconfined phase up here, they do see that there just seems to be some thermal dynamics, some sort of deconfined dynamics. But in the confined phase, they on the lattice, they do seem to see the lattice simulation explore the different, fuzzy sphere vacua as you sort of generate configurations. So that it's in there somehow. That fuzzy sphere dynamics is in there. Let me talk briefly, because I don't want to take up too much of your time. Let me talk briefly about high dimensional cases. So if we go to high dimensions, typically in lattice field theory, going to high dimensions it's obviously harder, but much harder because you get more points in your lattice. One of the problems is that typically you're interested in infinite space, like in QCD, and on a computer you have to make it finite. And so you have to worry about compactifying your space into finite volume and then worry about finite volume effects. Now, actually, in our case, it's much better because we can just put the whole theory, we can put the D-brane theory, the dual gravity, all at finite volume, and think of finite volume as another deformation of the theory in which to sort of understand what phases there are and so on. So it's actually sort of nicer in that sense. We gain a new coupling. So we have a one-dimensionless coupling here. Say in 1+1, we have a dimensionless coupling which was as before. That's the inverse of T, the size of the Euclidean time circle in units of the 't Hooft coupling. But now we have, if the theory is on a spatial circle of length L, we have another coupling which is associated to the size of that circle. So we can think of our theory living on a torus, a Euclidean torus, with couplings associated to each cycle. And there's a new observable now, which is the Polyakov loop around the spatial cycle. And again, that's got an eigenvalue distribution associated to it, which can diagnose certain phase transitions, large N phase transitions. So again, the eigenvalue distribution of this, depending on whether it's homogeneous on the circle or has some dependence on the circle, will diagnose whether we expect in the dual gravity the corresponding circle to be contractible or not, according to Witten. Now, it turns out that there is some interesting dynamics that we expect from gravity as we vary the size of this circle, and it's related to the so-called Gregor-Leflam instability. And it's an old story, and it's a rather complicated story, so I'm going to sketch it very, very fast here, and I'm happy to answer more questions on it if people are interested. But basically, in the Yang-Mills theory, you've got a circle. It could be large or small, by which I mean large or small compared to temperature. That's the scale to compare it to here. Okay, so we have to be in a regime where we want gravity to work, so temperature has to be small, but we can have a large or small circle in units of the temperature. Now, there is, let's focus on 1+1, then the natural dual, the original dual is some 2B gravity, and then there's some dual at finite temperature black hole, which is this D1 brane black hole. Now, that just trivially, when you wrap up the space into a circle, it trivially wraps over that circle. And in particular, there's no sense of Gregor-Leflam instabilities because this black hole carries D1 charge, which is string-like. And so you can't break a horizon which has a string-like charge. So there's no Gregor-Leflam instability here. However, because you have a circle now, you can T-dualize on that circle and go to some 2A theory in this 1+1 case. And now what was a large circle becomes small, and what was small becomes relatively large. And in the case of the large circle over here, well, this D1 charge, when you T-dualize, becomes a smeared D0 charge. And the point about D0 charge is now it can redistribute itself over the circle. And so it can decide whether it wants to be uniformly distributed or not. And that's precisely where Gregor-Leflam tells you that generally things want to clump, want to localize on the circle. And it turns out when you do detailed calculations, indeed here, their homogeneous phase, where it's like a string like this, is unstable to a Gregor Leflam. And really, it wants to localize. Now, this tells you that as you vary the size of the circle in the dual gravity, there should be some phase transition. You don't see it in this D1 or the 2B picture, rather. I mean, it's still there, this instability, but you can't see it as a supergravity mode, an unstable supergravity mode. It should be a string winding round the circle being unstable. But that becomes something you can see in the supergravity after a T-duality. And this localized phase here has been worked out in detail by George Santos in, again, very nice numerical GR work. And so actually the phase, all of these phases, the predictions, the gravity predictions here for the super-Yang mills have been worked out in detail. So it's much more complicated, and we have this interesting phase transition. And there are basically two phases we expect. And these, again, are associated to changes in the eigenvalue distributions of this Wilson line now on the spatial circle, our new circle. I really don't have time to discuss this. This is just when you, let me skip quite a few details. When you are in high dimensions, 1 + 1, 1 + 2, you have to worry about putting your supersymmetric theory on a lattice and preserving supersymmetry in the continuum. And there's a sort of old story now, it's quite 15 years old or so, on how to do that. And basically you have to cleverly discretize your theory to preserve some subset of the supersymmetry. In fact, just one supercharge is enough. And there are ways to do that. But if you don't do that in you can't just be naive in your discretization in 1 + 1, 1 + 2, because otherwise you won't get the right supersymmetric continuum. You would have to tune some operators. But nonetheless, that can be done. And something I should emphasize is that David Shake and de Grand some time ago took these sort of these formal lattice supersymmetric actions and put them into a publicly available parallel code that you can all download and play with if you want. And that's the code that we're using here. And just to sketch things, when we think about this, say, phase transition that I was just talking about, this Gregor Leflam phase transition, we have these two couplings, the size of the thermal circle, the size of the spatial circle. There's some region where gravity provides some good description of the, down here, this is where sort of alpha prime is strong. Up here, you have either a 2A or 2B gravity picture giving you a prediction. And there's this phase transition whose position is worked out in detail by George Santos and collaborators. And there's this is a large N phase transition between two different phases associated with different eigenvalue distributions. And starting with work with Anosh and more recently with Raghav and David, we looked at that 1 + 1 theory, and you can indeed see. You can try and estimate where this phase transition is by looking at eigenvalue distributions and Polyakov or Wilson lines. This is the gravity prediction up here. Really, for gravity to be good, you need to be working up here on your lattice. And it becomes actually difficult to extend into this region accurately. It was hard to identify where the phase transition was, so we get big error bars. But there's actually a phase transition in this theory which persists also at small tori sizes, which aren't described by gravity, but nonetheless there's some understanding of that transition, and it seems to interpolate across, and it doesn't look inconsistent with the gravity. But of course, it would be nice to do better and understand this better. But it's becoming more challenging in 1 + 1 and 1 + 2. One can also look at these two over here and over here, and actually look at the thermodynamics of those phases. And indeed, in the low temperature regime, where gravity should be good, you do see reasonable agreement or consistency with the gravity predictions, these dashed lines. And you also see by looking at these eigenvalue distributions on the circle that either at large n, as in this case, they're becoming more and more uniform, or they're becoming they're just tending at large n to some non-uniform profile, as one would expect. And finally, most recently in 1+2, we've also tried to extend these ideas. And we have some data now, which is, I mean, it's got pretty big error bars. 1+2 is very challenging. We could only get up to n of 8. Over here, we were able to get up to n of 16 in 1+1 using David and Raghav's very hard work and nice code. But here, only n equals 8. But nonetheless, we have some sort of consistency with the thermodynamics of D1 brain, sorry, D2 brain thermodynamics in the appropriate regime. And I really am way over time, so let me just summarize. So there's been sort of over the years some significant progress in trying to directly simulate these super Yang-Mills theory at finite temperature. I think it's reasonably clear in the quantum mechanics that there's good consistency with low temperature predictions from supergravity. It would be nice to extend to lower and lower temperatures and larger n, but at some point, I think the question there really is, what do we do next? At some point, you have to believe that it's probably true that the black hole is there. And then what do we want to learn? We can't learn about Hawking radiation and dynamics in this thermal setting, but maybe there's other interesting quantum gravity questions we can ask. So entanglement entropy, things like this. In the higher dimensions, it's still sort of early days. There's still lots more work that I think needs to be done to nail down these phase transitions and better see consistency. But you know, it's encouraging that that can be done. But of course, it's challenging stuff. Anyway, thank you. Sorry for overrunning dramatically.
Thanks, Toby. And thanks for answering and taking your time to answer all our questions. And
questions are great.
Okay, so it's now time for more questions then. So please go ahead and ask.
Hi, I had a basic question. It might be stupid. So just to understand these lower dimensional examples you mentioned towards the end. So you're studying 1+1 dimensional or 1+2 dimensional Yang-Mills theories on the lattice. Is that right?
Yes, that's right. So it's this maximally supersymmetric Yang-Mills. It's the theory that you would get if you took n equals 4 in flat space and just wrapped it up on, compactified it just classically on either one circle or two circles. Okay. It's that theory.
And the phase transitions in gravity you're talking about, so this is gravity in ADS space with some particular matter content, or what is the?
So in these cases, these are not in ADS because these are not conformal theories. So nonetheless, there's some gravity dual. It just has a dilaton that isn't constant. So there's some gravity dual that you can still work with. And the phase transitions, so that when the Yang-Mills theory is living on a circle, the dual gravity has a conformal boundary that also has a circle in. That circle extends into the interior. Right. And when you have a black hole, it can either the horizon can either wrap over that circle or it can localize on the circle, like in sort of Kaluza-Klein theory. And the phase transition between those is the phase transition that is predicted to be seen in the super Yang-Mills.
But then I just want to understand the action you use, for instance, is just Einstein gravity plus something else, or what is it that you're on the?
In the gravity, well, it's just 2A or 2B gravity, supergravity.
Okay, thank you.
Yeah. Yeah, I should say, I mean, those gravity calculators, I mean, finding, say if you've got the 1+1 theory, the simple finite temperature dual black hole in the 2B is just it's a trivial thing to write down. You can find it in the old papers. Everything just depends on one radial coordinate. It's very simple. It's just a solution of 2B. It's the finite temperature 2B black hole in this decoupling limit. But once you try and then find solutions where you have you compactify, compactifying a circle and that solution is trivial, it doesn't change anything. But if you then look for these other phases where the black hole has some interesting configuration on that circle, that's a very hard PDE problem, which requires numerical GR and quite tough methods to solve.
I see. Thank you.
But can be done. Yeah. In fact, maybe I should even make the comment that one of the things I found very interesting about this is that in some ways that's really quite a challenging numerical GR problem. And what's interesting is that you can get data from the lattice super Yang-Mills. We actually had data from lattice super Yang-Mills before there were these constructions of the gravitational solutions. So there were actually predictions for gravity from the lattice, for classical gravity from the lattice, which is a rather peculiar situation to be in.
Yeah, this is actually what sounded rather surprising to me, that that people haven't computed the supergravity, the corrections, is the alpha prime corrections, and
yeah,
no,
yeah, no, that's right. And the alpha prime correct. Yeah, so sorry, yeah, absolutely. Let me just I don't want to bore people. People should be free to tune out whenever they want. I could talk about this all day. So if we look at here, for example, coming back to your question, this is this leading black hole behavior, the T to the 14/5, which I've sort of highlighted in green. This is the lattice data, and it indeed comes down to it at low temperatures. This is in the quantum mechanics. So this is, I think, some of the best work in that quantum mechanics case. But what they then did in that work was to try and fit the subleading corrections in this power series in T, which you predict the powers from just thinking about high derivative alpha prime corrections. So you know which powers you should have, but you don't know the coefficients. But of course, by fitting this data, you can try and extract those coefficients. So here they're trying to fit these coefficients from the lattice data. So if you like, they're fitting some higher order derivative, they're fixing some of these higher derivative correction terms using the numerical data. And now, I think when they wrote this paper, they sort of said that what they were doing in doing that was quantum gravity. I would argue that they weren't at all doing quantum gravity. I mean, to me, the most interesting thing is understanding this leading thermodynamics, because that leading thermodynamics is black hole thermodynamics. And for me, that is quantum gravity. Black holes have thermodynamics precisely because of quantum gravity. Otherwise they don't, obviously. So what you're doing when you're understanding these alpha prime corrections is understanding string alpha prime corrections to quantum gravity, which to my mind is interesting. Of course, as a string theorist, it's interesting, but really, my sort of primary goal would be to understand quantum gravity rather than particular stringy models and their corrections. So I think whilst these corrections are interesting, and it would be very nice to be able to calculate the coefficients so that one could check agreement. Again, I think, as you say, it's surprisingly hard to do, and I don't think it's been done. I think it's hard to do because you're in these Ramond backgrounds, and so I don't think it's well understood how to do those calculations. But of course, it would be interesting to check. Yeah.
Even to obtain the higher derivative corrections, it's hard to get this higher derivative correction explicitly.
To get the coefficients, yeah.
So, but in the context of say black hole entropy counting, people have actually done this alpha prime corrections, right? And checked matching and all this. So
yeah.
This is the part of the black hole entropy success story, to take into account this walled entropies systematically.
Yeah. So I mean, that's right. I have to say, I don't know enough about what is known about alpha prime corrections in the different various backgrounds. So here again, you've got this running dilaton. You have the Ramond fields. So I'm not sure. I think it's a more complicated situation than in other settings where where typically you have some extremal black holes. When you have extremal black holes, you typically have some nice near horizon geometry, some ADS2 cross, near horizon geometry. The dilaton will typically be some constant, and so understanding alpha prime corrections, I think, is much simpler. I think it's Yeah. So I have to say I don't know enough about it.
Thanks. More questions? Okay, so maybe I asked a very naive question. So you said the entanglement entropy is obviously hard to compute on the lattice, but to understand, for example, where the horizon is or something like that, one could simply compute Wilson loop or something of that kind.
Yes, so I didn't mean to say entanglement entropy was hard to compute in the lattice. I think I meant to say these higher dimensional theories like 1 + 1, 1 + 2 are quite hard. They're hard to study at large N. Entanglement entropy hasn't been computed in these situations. And so I actually don't know how hard it is to compute on the lattice. I think it's an obvious next step in this program. So there was a nice paper by Mark van Ramsdonk and collaborators talking in the quantum mechanical case, the Bfss case, about what entanglement entropy would look like. Because of course there you don't have space, right? You've only got time. So what is the entanglement entropy that you're computing? Well, it's the entanglement of the various matrix degrees of freedom with each other. And how do you characterize subregions of these matrix space that is relevant for understanding gravity? So they have some proposals for interesting subspaces within this sort of matrix degrees of freedom that could be relevant to understanding the dual geometry and extremal surfaces in the dual geometry. Now, how that's relatively recent and no one's done any calculations yet. So I don't know how easy it is to calculate, but I think it's an interesting thing to look at.
Yeah, but roughly speaking, one easy way to see the horizon, say for p = 1, would to simply look when you are getting this linear growth of entropy, right? This, I mean, if you have just an interval, then when the entanglement starts growing linearly with the interval, that is when you would say that you're sort of seeing the horizon, right? And so, yeah, so in a way that is another way to check whether you have a horizon or not, right? In
yes,
a way.
I see what you mean. Yes, absolutely. Yes. Yes. So I think, yes, absolutely. That's right. No, I agree. So yes, I mean, I expect that's quite difficult to do in the 1 + 1 setting, but I think it may be possible to do something in the quantum mechanics case, but unfortunately not entanglement in associated sort of spatial region. You see, one of the problems with the spatial region is that, of course, on the lattice, your lattices are typically not that big. So, you know, in our 1 + 1, 1 + 2 work, we were working with sort of maybe 16 cubed lattices. And if you've only got 16 points in each direction, you haven't got many choices of interval to think about. But it may be possible. It may be possible to do some calculation.
Okay.
Yeah.
Okay, so thank you, Toby, for this great colloquium.
Okay, thank you. I'm sorry to have gone on, but it's very nice to have the questions. So thank you for your questions.
Yeah, thank you very much. So have a very nice day. And
you too.
And have a good week, everybody else. See you. Bye.
Bye.